Okay, so now we're going to start to review the Laplace transforms. So you might remember them from your differential equation class. If not, we're going to talk about how we use them. I'm going to skip ahead of some of the mathematics, how they work, because we're engineers, we just want to use the math as tools. And Laplace transform is a wonderful tool in order to solve the ODEs that we're going to see in a lot of our systems. So let's say that we want to take the Laplace transform of some function phi of t. What that means mathematically is we're going to integrate from 0 to infinity e to the negative s times t times our function of t with respect to dt. And that's going to give us phi of s. Typically what we're going to do is if something is in the time domain, then we'll have it as a lowercase letter, so lowercase phi of t, and then if it's in the Laplace domain, it'll be capital phi of s. And s is just the Laplace factor. It's complex, so it represents more of frequency rather than time. So it's a complex variable to the negative t, I believe. And that's where the math is rough, and that's why I'm reviewing these videos before class. So we've got this Laplace factor, and what's nice about the Laplace transform is we're taking ourselves out of the time domain into the frequency domain, and that's going to have a couple of convenient properties. So the reason we do this is because, one, we have the property of superposition. And that's going to say that if we take the Laplace transform of some function f of t, it becomes f of s, some function g of t, it becomes g of s. Then with superposition, the Laplace transform of a times f of t plus b times g of t is equal to a f of s plus b g of s, assuming a and b are constants. So there's a lot of flexibility if we have a huge function. As long as if it's a linear function where we can treat everything individually, we can take the Laplace transform pretty easily and go between the Laplace domain and the time domain fairly easily. Second thing that's nice about Laplace domain is that derivatives are simple. So if we take the Laplace transform of the derivative of phi, that's going to be s times phi in the Laplace domain minus our initial value of phi. We see similar things with integrals. If we take the Laplace transformation of the integral of phi, then that's just going to be phi of s divided by s. And whenever we have our mass spring damper, we saw that we had velocity and position, so we have to deal with multiple derivatives, and that they're equal to acceleration. So let's do a quick check-in. What exactly would the Laplace transform of a second derivative be? So if we want to find the Laplace transform of acceleration, that would be convenient to know. So we can do this manually and say that it's s times the Laplace transformation of velocity minus our initial velocity, and then take that a step further and say that that's equal to s squared times our position in the time domain minus s times our initial position minus minus our initial velocity. Or in this case, if we're using phi, s squared times phi of s minus s times our initial phi value minus the initial first derivative of phi, initial value of the first derivative of phi. This will make a lot more sense when we start to go through examples, but it's just a nice thing to remember. You can start to see a pattern where it's going to be s to the power of however many derivatives you have, and the initial conditions will follow suit. You don't have to have it memorized because not something you would need memorized, but it's a convenient thing to know. So now what we want to do is we want to use the Laplace transform to solve ODEs. So you should have learned this in your math class. It's a prereq for this course, but let's go through the steps one more time. So we have some sort of differential equation that we want to solve, and we know that we can solve it by taking it to the Laplace domain. So let's go ahead and do that. So we'll take the Laplace transform of our differential equation. We're going to use superposition to make it easy. And we're going to end up with a bunch of polynomials of s, because every time we have a derivative, it's going to be multiplied by s or s squared, and however many derivatives we have. So we're going to want to simplify and express our unknowns in terms of functions of s. So we want to say x of s is going to be equal to something, and that something might be a little bit of a mess, but we want to isolate our unknown variables. Then we're going to use partial fraction expansion in order to further simplify our polynomials, to figure out what x of s is in a way that we can use our Laplace transform table to bring us back to the time domain. Let's give a better example for that x of s, though. So we want to have it in simple terms. So let's say that we have maybe s times something in the top, s plus a, s plus b, s over s plus c, s plus d. Maybe there's a lot more of that. We're going to want to get it into terms of a over s plus g, b over s plus b over s plus h. Again, this one abstractly is a bit complicated. We're going to go through some examples in the next video. But we use partial fraction expansion to put it into a format so that we can take the inverse Laplace transform table. And inverse Laplace transform table, we're going to go to that same table that we will use to put ourselves in the Laplace transform and bring us back to the time domain. And what that's going to allow us to do is it's going to give us x in terms of t, and we get that function where we have x in terms of t in terms of any inputs and initial conditions. So next video will be an example, and that'll go through how we solve these ODEs.